Hi guys, welcome back to Data Every Day. Today we are looking at a data set of resumes. So I think it's a synthetic data set of skills extracted from fictional resumes. But in this CSV file here, we have a bunch of different features about a given candidate's skills. So there's 224 columns here. I think up here it says there's 218 skill features and then 4 demographic features. At the beginning we have this like duplicate index column. So almost all of these are going to be used as features. I think 222 of them. So that is quite a good number of features to use. However, this is quite a sparse data frame because they are all binary features, 0, 1. The only values they take. We are going to try to use dimensionality reduction to try to retain as much information as possible but reduce the number of columns. So let's hop into the notebook. We're going to import NumPy and pandas for working with the data. For pre-processing, we'll use the train test split function and standard scalar from sklearn. And I guess we can include PCA because PCA is what we'll use for the dimensionality reduction. That's the principal component analysis, all from sklearn. Our models also from sklearn are going to be the logistic regression, decision tree classifier, and random forest classifier. Notably, the decision tree is notoriously prone to overfitting, so we might actually see a performance increase when we reduce the dimensionality of our data. So let's go ahead and import all of that and load in the data using pandas.readcsv. So we're going to grab the file path to the CSV file up here. I'm going to go ahead and copy that. It's this one right here. Paste that in and take a look. So here's the data set as we saw before. Now I can't see all the columns. I don't know how important it is to, but if you want to, we can go in and say pandas.set option max columns none. And what that allows us to do is see all 224 of these columns. And they're all binary like we saw. Now we could do data.info, but we don't really get much information from that because it doesn't show all the columns. There are 5 integer columns. One is the index column here that we're going to drop, just a duplicate, or corresponds to some sort of ID for each applicant. And then at the end we have these 4, which are also integers. I'm not sure why these are encoded as floats in the middle, but they're all binary features. Alright, so let's get into pre-processing. We're going to create a function called preprocess inputs that's going to take in a data frame, and this is just going to copy it over for now. And we can get the processed version of the data back in X, pass in data. So this is the copy that we're going to perform the preprocessing on. So there's really not much preprocessing to do. All we have to do is go ahead and drop the index column. That's df equals df.drop, and it's called unnamed 0. And we're dropping from axis 1. Alright, so it's gone, and we no longer have it. There's no more pre-processing to do. This is all valid columns to pass into our data, into our models. So let's split and scale. We're going to split the data frame into X and Y. Y is what we're trying to predict. That will be the interview column. This column, I did a little digging. It seems like this column means whether or not the applicant passed the interview. Again, this is a synthetic data set, so we can expect you can usually expect good results from a synthetic data set. It's not realistic though. So we'll try to predict this, whether it's a 1 or a 0. And I believe that means a 1 is they were accepted and a 0 means they were rejected. So let's go ahead and set the interview column into Y, and then X will be the rest of the data. We'll drop interview from axis 1. And then let's just return Y, X and Y and get them back. I guess we can do the train test split actually. Train test split. This is where we split the data into X train, X test, Y train, and Y test. And why don't we send 70% of the data to the train set? So we will use the train test split function from sklearn, and specify our train size. So we're splitting x and y, and then our train size will be 0.7 for 70%. Shuffle equals true, so it'll shuffle the data before it makes a split, and then we'll give it a random state so we can ensure the shuffle is always done in the same way. And let's go ahead and return these 4 values here and get them back over here. Alright, so xtrain should be 70% of the data and should no longer include the interview column. And it looks like that is correct. Okay, ytrain is just the label, so these are just ones and zeros. And we can see the class distribution with ytrain.value counts. So we have a slight imbalance, nothing crazy, not a cause for concern, I don't think. Let's go ahead and start training. So I'll say training and results. We'll just put them in one block here, or a few blocks. We have to scale the data before we pass it into the models. For the decision tree and random forest models, we don't need to scale, but for logistic regression, we do. The performance will be greatly increased if we scale the data. So let's create the scaler. We'll say we'll scale x. So our scaler will be a standard scaler, which we imported earlier from sklearn, and that will give every column a mean of 0 and a variance of 1. Now all the columns do take the same range of values, but actually when we do the principal component analysis, we do need to have the values centered at 0. That's one of the prerequisites. I'm not sure if the sklearn object automatically does that for you, but I'm going to do it anyway beforehand. So let's go ahead and so I'm going to scale it before. So let's put it up here actually. We'll put it in the function scale x. So our scaler is a standard scaler, which gives every column a mean of 0 and a variance of 1. And we'll fit the scaler just to the train set, because we want to pretend we don't have access to the test set when we're doing the pre-processing. And we'll create xtrain. We'll overwrite xtrain with the transformed version of it. So we can use scaler.transform to scale xtrain and pass it back into the variable. However, this returns a numpy array, so I'm going to go ahead and turn it back into a data frame after, keeping the indices the same as they were, and the column names the same as they were. Alright, let's go ahead and copy this over for xtest. Alright, and we should have scaled data now. So they now all have mean 0, variance 1. And that's the same. Okay, so let's create our models. We're going to create a dictionary. We'll put the name of the model on the left, logistic regression, and then we'll map that name to the actual instance of the model from sklearn. So we'll do it for decision tree. That'll be our decision tree classifier. And then we'll do random forest. That'll be our random forest classifier. Alright, let me just indent these up so they're even. It'll make it easier to see the results later. And then we'll print out, what we'll do is iterate through for name and model in models.items. Then we'll fit the model on the train set, xtrain, ytrain. And we will print out a little message that says the name of the model followed by a message that says it was trained. Alright, so let's run that. They've all been trained. And let's get the results. So for name and model in models.items, we will print out the name of the model followed by the accuracy displayed to 2 decimal places and as a percentage. So we'll then format this using model.score to get the accuracy value on the test set xtest, ytest, and we'll multiply the accuracy by 100 so that we can see it as a percent. Alright, there are the results. So they're fairly good. It looks like the logistic regression is beating out the tree models this time with a 96% accuracy for right here. Alright, so let's do the dimensionality reduction. So we'll say training and results with dimensionality reduction. So we'll create a new PCA object. Actually, let's say Okay, let's create this variable called nComponents. This is going to be how many features we want to reduce the dimension to. So why don't we do 2? So we'll just bring all these 222 columns down into 2 columns. So the way PCA works, let's create the PCA object and pass in the nComponents here. The way this works is it basically changes it changes the way you look at the data. So you can think of each of these columns as being a vector in 222 dimensional space. If you consider the shape of the data in 222 dimensional space, which you can't really visualize, but if you can just imagine, it has some sort of shape in space. And the way the columns are like the basis of the space. So it's like, where are your x-axis, y-axis, z-axis, up to 222. If all you do is shift the axes, the basis, to match up with the shape of the data, so that the axes line up with the direction of greatest variance in the data, then you have an axis or a column that now describes more information in the data than any one of the original columns did. So the idea behind principal component analysis is to change that basis so that your first few columns contain a huge amount of the information in the data, and usually it tapers off after that. So let's go ahead and fit this PCA object to the train set. We don't have to do it for y, just x. And why don't we'll just use fit transform, I guess. So actually no, we'll use fit because we gotta do it on the test set also. So we fit to the train set and we transform the test set. So let's call it xtrain reduced and use pca.transform on xtrain. Now this also returns a numpy array, so I'm going to go and turn this back into a data frame. Now the index will be the same as xtrain, and the column names are going to be PC1. Well, actually, why don't I do this? I'll do PC plus string of I for I in range 1 until nComponents plus 1. And what that'll do is just name the column names PC1, PC2, PC3 up until whatever nComponents we have. Why don't we keep nComponents to be 222 to start with? Alright, so we'll copy this over for xtest. Call this xtest reduced. I'll just go and grab all these. There we go. Let's look at xtrain now. Xtrain reduced, I mean. So these new columns are the principal components. And at a glance, you can't really see what's going on here. But if we look at pca.explained variance, these are the variances of each principal component, starting with PC1 all the way until PC222. And you can see we have a large amount of the variance is contained in the first number of features. And down here we have very little variance. So we've shifted the basis of the space to match up with the directions of greatest variance. We can also do explained variance ratio to see the percent of variance in the columns. So there's 2% here, 1.3% here. Let's just see how this affects the model. And the idea behind the dimensionality reduction aspect of this is we can drop all these columns because they have such little variance, such little information in them, and just hold on to the first few. Alright, so why don't we let's just train. So we'll create the models again, but this time we won't train on xtrain, we'll do it on xtrain reduced, and then we'll get the results over here, this time on evaluating on xtest reduced. Alright, so wow, that's very interesting. Very interesting. We didn't actually drop any data. We still have 222. We don't have any loss of information. All of the information is still in the dataset. All we've done is change the perspective of how we look at it. However, we're actually getting better performance in the tree models than we originally did. You can see the logistic regression model is unchanged, same as before, but our tree models accuracies have gone up, which I'm not sure exactly why. That's very interesting. But now let's see what happens when we reduce the dimensionality. Let's say we bring it down to 20 features. Now extreme reduced, all that did is drop those remaining principal components, and we now have only 20 columns, but hopefully we've retained most of the information in the original data. Let's go ahead and retrain and check. And wow, we're actually getting decent results, right? So we lost like 180 columns there, 140 columns, but we are still almost as good on the logistic regression, and we're still doing better on the tree models. So like I said, the decision tree is very prone to overfitting, so reducing the number of columns definitely we could see as having an effect. But what's interesting to me is that, you know, even just changing the basis had a great effect. Alright, so why don't we bring this down to 2. So we only have 2 columns. Let's see how this does. Train and check. And we're actually still doing quite well. 94% accuracy on many of these columns. Using only 2 features. Only these 2 features, and we're getting nearly the same results as we originally had with 222 features. So let's see 1. How does that look? We have only 1 feature. Yeah, that one dropped the performance, but 2 features seems to be enough to retain a good portion of the original accuracy. Let's see, I think 3 probably will give us a little more. Yep, and what about 5? I want to find that sweet spot. Yeah, 5 looks pretty good. You know, I think we could probably push it, but that should do it. So that will sum up today's video. Thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.